Hey guys, Butch here. Welcome back to Hardware 3D Tutorial 48. Today we're going to be talking about the render graph. We're going to be developing a system that will allow us to automate many aspects of a render graph. So the first question is, well, Chili, what the heck is a render graph? Render graph is just basically it's a graph of all the different passes that you do to render a frame. So if you think back to the system that we created in the previous video, we've got a pass that does our normal geometry rendering with Phong shaders. Then we've got a pass that draws outlines, blurs those outlines, and then composites that back on to the original scene. Those are all different passes. They connect to each other, right? The resources from one pass are passed to a different pass, or passes both draw to the same buffer and they have an ordering. That's the concept of a render graph. Don't get it mixed up with a scene graph. Scene graph is the geometry of the scene, right? You know, you've got a car and it's got two child nodes that are the two characters sitting in the car. It's a completely different idea than a render graph. Don't get them mixed up. Scene graph is geometry. Render graph is passes and resources. So today we're going to be talking about this render graph system. It's a solution to a problem. We should probably talk about what that problem is. So here is the render graph for, AAA game people are probably aware of, Battlefield 4. Look at how many, passes an ambitious game performs in a single frame. That's a lot of passes. It's a lot of resources to manage, a lot of pipeline settings, a lot of commands to make. These passes, they all depend on each other. Maybe one pass renders to a texture, and that texture is used as an input to the next pass here. Now, of course, every different game is going to have its own different, set of rendering passes. It's going to have its own unique render graph. But even within the same game, you're going to have different render graphs for, depending on whether you're rendering UI, or maybe you've got like a combat mode or an overworld mode. You're going to be doing different rendering for cutscenes. Even within the same scene, as an effect is activated or, maybe an area changes, your render graph is going to be dynamically changing. And it's really hard to get all these different, dependencies and everything correct if you are just, hard coding everything in a single monolithic, function. You know what I'm talking about here. I'm talking about like our frame commander. It's just a very simple, it's got an execute function, and it's just a very simple linear script that does a bunch of commands. And that works fine enough for simple things, but when things get complex, this is dumb and this is bad. And every time you have to change something, you risk breaking everything and, not having a clear idea of what was broken. Like imagine this, but it's not, like 3 or 4 passes, it's 100 passes. It's not going to be very nice to work with. And every time you want to use the same pass in a different render graph, you're copy and pasting code. It's terrible. So instead of scripting the procedure for each pass in, just one big monolithic procedure, we want to make smart pass objects that encapsulate and automate all the necessary actions that need to be taken. They can internally handle the resource allocation. They can free the resources when they are destroyed. They will announce sources and sinks for resources that can interact between more than one pass. So they say, okay, I require these resources to be connected in from a previous pass, and I provide these resources that subsequent passes can use. And when we do this, passes become self-contained building blocks that can be plugged and arranged in different graphs without the need for rewriting logic or copy and pasting. And then when you have these passes, factored out as their own separate classes, when you improve a pass, all the render graphs that use that pass automatically get improved, which you wouldn't get if you just copy and pasted all that code everywhere. All right, so let's look at a top level diagram of what a render graph is going to look like in our system. You've got the render graph here. It contains passes, which are these, blocks here, these squares. And it also contains like global resources. So you take a look at these green boys here. You've got like the back buffer, the depth stencil. Those are just kind of global resources that are chilling out that are going to be passed into our passes here. Now the passes themselves, they contain the resources that they're going to use, and they encapsulate the logic of how to bind those resources and what draw calls to execute basically. And what they do is a lot of these resources, they don't actually own themselves. They have to borrow from somewhere else. So if we look at these two passes here, what these boys are doing is they are clearing buffers. So this one's clearing the render target, this one's clearing the depth stencil. So it needs to take in a render target and a depth stencil. and it will perform a clear on them. And it provides then after that, those same targets to be passed on to the next. So they kind of like a pass through. They borrow and then they pass it down the line. And then here we've got our standard Lambertian rendering. We do the Phong Shading. So that requires a render target and a depth stencil. And it will execute all the binds and it will do the draw. Now these circles you see here, very important part of the system. They're called sources and sinks. And what they do is they advertise resources and they give them names. And that allows the system, the whole render graph system, to connect them together, to basically link the render graph together. So from this diagram, you see the major players of our system here. There's of course the render graph. You've got your resources here. You have passes and you have sinks and sources. So let's take a look at each of these different components in detail and how they come together to form a working system. So first, let's take a look at the anatomy of a pass. There's going to be a base pass class, and that holds all the boilerplate and provides the general interface for all the different specialized kinds of passes to conform to. So this tells us the things that every pass is guaranteed to have. And some of those things, the data, is the name. Every pass has its own unique name. You're not allowed to have two passes in the same render graph with the same name. That would be ambiguous. And every passes advertises its sinks and its sources. The three key functions here to look at are execute and register sync and register source. So what a derived pass is going to do is in its constructor, it's going to register the sinks and sources that it advertises to the render graph. It tells the render graph, you got to hook these guys up. And in its execute function, the virtual function here, it is going to describe all the things it does when it's going to be executed, right? The things it has to bind to the pipeline, the commands it executes, etc. So if we take a look at register sync and register source, you see what it does here. It basically just pushes them back into those containers, but we're also going to check to make sure that we don't have, a sink, two sinks or two sources that have the same name. So now let's take a look at a very simple pass, the buffer clear pass. It does what it says. It clears, Z buffer or a render target. Here we declare a resource that this pass is going to be managing, and that resource is a buffer resource. Notice that we manage our resources with shared pointer. This is pretty much throughout the entire system here. And the simple pass only needs to implement two things, the constructor and the execute function. And the constructor is very simple. It just registers a sink and a source that are both connected to that buffer. So we can see here the managed resource, the buffer, is linked to this sink and is linked to this source. They both have the same name, and that's fine. Sink and a source can have the same name. You just can't have two sources or two sinks with the same name. So here we register those sources and sinks, and then for the buffer clear pass, it's very simple. You just call clear on that buffer. And what buffer gets cleared, again, that depends on, what is linked to this. So we're linking this same class to two different buffers in a single render graph. So the single component can be used in many different places, can be used with different resources, can be used multiple times in the same render graph, no problem. This binding here happens at runtime. Now, most of the passes that you're going to be writing, they won't inherit directly from pass. They're going to inherit from one of the more specialized children of pass. So, if you look at Lambertian pass, this one inherits from render queue pass, which makes sense because, a Lambertian pass, it's going to have a render queue. And there are going to be jobs submitted to that render queue, and then the pass is going to execute those jobs. So I define a small hierarchy of base pass classes that you can inherit from, and they just add, boilerplate functionality that some passes will want. So, you could obviously, like we saw before, inherit directly from pass. Many passes have a container of bindables that they register in, and then they want to bind them all every time they execute. So I call that a binding pass. Maybe all the draw calls in this pass, they all use the same blending mode. So we can just put that in a container of bindables that are just run through and bound every time we execute this pass. Now, among the binding passes, there are two more specialized versions. One is the render queue pass, which, has a container of jobs, and jobs are submitted to it. And then when you execute it, you're going to execute all those jobs. So this one adds boilerplate for the render queue. The other kind of binding pass is a full screen binding pass. And this one has, stuff needed to do a full screen, post-processing filter. Stuff like the full screen geometry, the textured quad. So instead of having to declare, that stuff for every single full screen pass you have, you can just inherit from this one. You get that boilerplate automatically. Very nice and clean, very dry. So if you look at the bindable pass, it inherits from pass, and it adds a container of binds. It adds some functions to add a bind to the container, a function to bind all these guys. This will be called usually from the execute function of whoever inherits from this. Since all binding passes, they generally use a render target, right? There's no sense in binding things to the pipeline if you're not going to render. So they're going to use a render target and or a depth stencil. So I just add those in here as well. And there's a function here to add a sink that connects to one of the bindables in this container. And that's a little tricky, so we'll come back to that later on. But yeah, generally this just adds stuff, boilerplate, to give you a nice container of bindables. The actual implementation of those functions is pretty self-explanatory here. Note that either the render target or the depth stencil might be null. So if the render target is null, we're just going to bind the depth stencil alone. If the render target is not null, we bind it with this depth stencil, which may or may not be null, but that still works. It's just you can't, call a function on this if it's null. So you got to do that test in there. And then if we look at the render queue pass, it has a vector of jobs, can accept a job, and it also provides some execute functionality, which again will just bind all of the bindables in the bindable container and then execute all the jobs. So it's fairly simple boilerplate here. But it's nice to be able to just, inherit from render queue pass and get all this stuff. You don't have to, copy and paste it for every different pass that you create. And if we look at the full screen pass here, it doesn't really add anything new to the class, but it does set up a bunch of boilerplate for you in the constructor. So if we look here, it creates all that full screen geometry for you. Every full screen pass is going to use, the same kind of vertex shader input layout. So it just puts all that stuff for you into the bind container. And a lot of full screen functions, all they're going to do is bind and then draw. So it gives you that too. But if you need to, of course, you can override this. It's a virtual function. But yeah, these four classes here are what you can inherit from to create your various passes that you might want to create. And so for example, let's take a look at a Lambertian pass. What does it do? Well, it's very simple. You would just inherit from render queue pass, and you have most of the things that you already need. So all you need to add is a constructor that sets up all the specific things you need, all the resources. Now, it just so happens that most of the bindables for the Lambertian pass, they're handled in, the drawable and in technique. So we don't actually need to put many bindables in the container. We just got to announce, we have to advertise our sinks and sources, our inputs and outputs. We need a render target and depth stencil, and we provide those things to the next thing down the line if they want it. And the only thing we really add here is for all the drawing in the Lambertian pass, we're turning stenciling off. So that's the only, bindable that is constant throughout this entire pass. But yeah, it's the pass library in a nutshell. Here's the outline drawing pass. Again, it registers sinks and sources, render target, and depth stencil. That's pretty standard. But now for the outline drawing, many of these things are going to be common for all the draws. So for example, outline drawing is, it's going to be solid rendering. So it's going to use a solid vertex shader and pixel shader for every draw call. And masking, it's going to be generating a mask here. And for the rasterizer, we're turning off two-sided drawing. But yeah, because a lot of the boilerplate is handled for you, a lot of the time when you want to create your own pass, you just inherit from the thing that makes the most sense. In this case, outline drawing pass is a render queue pass, so you inherit from that. And then you set up your sinks and sources and any resources that you need. Now, one of the big elephants in the room, obviously, is, how do these sinks and sources actually work? And we'll get to that. But first, let's pull out and look at the big picture again. So let me show you what it looks like when you define an actual render graph. So this is the blur outline render graph. It has, quite a bit of passes. Let's take a look at the diagram for this. So this is what the blur outline looks like. Again, we're going to clear the render target and the depth stencil. We've got our normal Lambertian pass. we're going to generate our mask, stencil buffer mask, here. This pass draws the outlines, the solid shading. We do the horizontal blur. We do the vertical blur that is going to composite together with our Lambertian result and is going to use the outline mask, and that gives us our final result. I mean, compared to Battlefield 4, it's not that complicated, but you can see here, even with just this simple setup we got here, there's already a lot going on. So now, how does this look like in code? Well, here it is, the blur outline render graph, and most of that setup is going to happen in the constructor here. And you can see here right away, it's a very regular system. Follows a set pattern, which is very nice going forward in the future. But yeah, what we do is we create a pass. Passes are created as unique pointers. So here is 2 buffer clear passes for clearing the render target and clearing the depth stencil. So you create a pass of a specific pass class, and you give it a name. That's the name that you're going to use to refer to it within the render graph. Once you have your pass, you have to set the linkage. So passes have sinks, and you have to tell that pass what sources each of its sinks is going to target. So we say here, okay, so the buffer in clear render target, this sink is going to target the back buffer in the global space of sources. So that's this boy right here. These are the global sources. So clear rt.buffer targets global back buffer. And then once you set up those targeting, you add that pass to the render graph. And there you go, you've got one pass in. And then we also do that for the clear the depth stencil. The Lambertian pass, its render target sink is going to target the output or the source from clear render target. And the depth stencil sink is going to be sourced from the clear depth stencil buffer. So here you kind of see already how sources and sinks work, right? They give us names that we can use to describe the linkages between passes. And then the machinery of the render graph system will hook those all up with the smart pointers. But the procedure is always the same. You create a pass, give it a name, you set its sync linkages, and then you add that pass to the graph. So with that information, let's take a look at what sinks and sources are all about. So if we look at the base sync class, it has 3 pieces of member data. First member data is its registered name. So this is the name we would use in the render graph if we ever wanted to refer to this sync. And then these 2 down here, probably could have named them better, but this is the name of the pass that this sync targets, and this is the name of the source in that pass. So this is how the render graph can determine, what source should be connected to this sync. And then you've just got, basic getters and setters and some virtual functions that will be implemented by the things that inherit from sync. Now, the actual concrete sinks inherit from the base class, and you'll notice they're all templated. And the reason for this really strikes at the heart of how this system works. So the basic idea is, we've got a pass. This pass it embeds a shared pointer to some buffer that this pass is going to work on and forward to subsequent passes. All right. But it doesn't actually own this buffer concretely. When you add this to the render graph, the linker has to get an actual buffer and fill this shared pointer with a reference to that buffer. And it uses the linkages from the sinks and the sources. So you have this thing has a sink, and that sink is targeting the global back buffer. So when you add this, the render graph is going to look through its global sources. It's going to say, oh, I found it. Okay, what next? Well, now we know that this sink matches this source. Now this source has a reference to the shared pointer that owns this buffer resource, has a reference to this shared pointer. And this shared pointer is actually filled with a concrete resource. This shared pointer has nothing right now. This sink has a reference to this shared pointer. So what we do is then, once we know this linkage, these sinks and sources, they basically communicate with each other. And this reference is used to copy the reference to this resource into here. And so now this shared pointer is referencing the same resource as this shared pointer. So the sync source linkage is used to basically orchestrate the filling of these pointers. And now that this shared pointer actually owns something, that can be forwarded down to the thing that links to this boy. Now here's the trick. Here's the catch. So these sources and syncs, they need to reference the shared pointer itself so that they can fill it. Well, at least this one needs to reference a shared pointer so it can fill that pointer. But shared pointers are templated types. They're not runtime polymorphic, they're static templated. So if we want to get a reference to that, then that reference is also going to need to be templated. And that's why we see that this is a template class T. It's basically templated on the type of the shared pointer that it's going to be working with. So we can see here, the direct buffer sync has a reference to a shared pointer. That's the thing that's actually going to be linked. So when we make a sync, we pass it its name, and we pass it a reference to the shared pointer that it is going to be filling. I mean, this is just a helper that calls make unique, and it calls this constructor here, which is very simple, just fills the name and it fills that reference. And the actual magic happens here with the bind function. So when the render graph figures out which source is connected to which sync, it calls bind on that sync, it passes in the source. We call yield buffer on the source, and what that's going to do is that is going to get a shared pointer to the resource. We try to cast that with a dynamic pointer cast to the type of pointer that we're binding to. This allows us to do some, polymorphic stuff. Because you can see here, this function, yield buffer, it always returns a shared pointer to buffer resource. But maybe we want our sync to only work with render targets or to only work with depth stencil. So we do this dynamic pointer cast to make sure that it's the right type. If that fails, this is going to be a null pointer, and then we're going to throw an exception, give ourselves some good diagnostics, telling the programmer that the render graph that they've specified doesn't make any sense. But if it doesn't fail, then we just do a simple move of the shared pointer, and we set the linked flag to true. And then we're done. And that's basically how it works. The render graph uses the names in the sync and source and the names of the passes to match syncs and sources together. And then it calls bind, which just fills the pointers. Now we can see here that there's direct buffer sync, there's container bindable sync, and there is direct bindable sync. So there are buffer syncs and bindable syncs. And in the bindable syncs, there's a container version and a direct version. And the reason why that is, that I'll leave for a little later in the video. It's not that important right now. But yeah, that's syncs in a nutshell. And then once you understand syncs, you're already halfway there to understanding sources. A source just has a name because syncs target sources. So sources don't need to target syncs. You don't have to do it both ways. One is sufficient. So a source just has a name. It has these yield functions, which yield the shared pointer, basically getting another reference on the resource. And again, the actual concrete classes are templated because you need that reference to the shared pointer. Make function is the same idea, calls make unique with the constructor here. And then yield buffer, and all it does is it just makes sure that you haven't already bound it somewhere else. And then it returns a shared pointer copy, another handle on the reference. So that's the basic concept of the sync source system. So we've looked at passes, we've looked at syncs and sources. Now we just have to look at the actual render graph. I showed you a derived render graph, but I haven't shown you the actual base class yet. So here is the render graph base class. Now the most important function here is Append Pass. This is what you use to add the passes to the render graph. And when you add a pass, that is when all that linking happens. So this is by far the most important function. And this function here we'll call this private helper function link syncs. So let's follow the trail. We're going to follow the chain of causality here. So when you're adding a pass, you're going to create the pass. You're going to set the targets, right? Then you're going to add that pass to the render graph with Append Pass. What happens then? Well, the first thing you do is you check to make sure that the name of that pass hasn't already been used. If so, that's a problem. Throw an exception. If not, then you're going to link the syncs of that pass. And then finally, you're going to push that pass into the container. So what are the syncs? How do you link the syncs? It's very simple. You loop over all the syncs in the pass. For each sync, you get the name of the pass that it targets. Now, if it's targeting a global, you're going to loop through all of the global sources, check to see if the names match, and if so, you're going to bind them. If you loop through all the sources and it still hasn't been bound isn't true, you're going to throw an exception because every sync must be connected to a source. You can't have unbound syncs. That's a problem, at least in the current system. In the future, it might be optional, but for right now, every sync must have a source. Now, if it wasn't global, then you're going to look through all the passes, find one with the matching name, then get the source in that pass that matches the target source name, which I named output. This is a complicated thing. There's a little bit behind the scenes, but this system underwent a lot of refactoring. And originally, it wasn't syncs and sources, it was inputs and outputs. But that started to get confusing for reasons, which I won't go into here. So I renamed it sources and syncs, but apparently I missed a spot. It's still called get output name, but doesn't matter. Once you found the correct pass that you're targeting, you get the source in that pass. If it doesn't exist, by the way, this will throw an exception. But if it does exist, you bind it, and that's it, you're done. What I should do here, and what I think I missed, was if I loop through all the passes and I don't find one with a matching name, I should also throw an exception here. So here, I should have exception code that's basically the same as this code here. But I forgot it. I have to add that to the to-do list. But anyways, that's what you do. So this is the part of the render graph that resolves the names and calls the binds. And you've already seen the bind calls. They just fill the pointers, right? And that's really that's the meat of this whole system here. Besides that, what else do we got? Well, we got the execute function. All that does is it loops through all the passes and it calls execute on those passes. Simple enough, right? A reset function calls reset on all the passes. You might be wondering, what does a reset function generally do? Well, I mean, if you look at a render queue pass and you look at reset, all it does is it clears the job queue, getting it ready, emptying it so that the next frame you're not going to redo all the same jobs that you did before. I haven't gone over it, but I mean, the data is very simple. You got a container of passes. You've got containers for global syncs and sources. And every render graph is guaranteed to have a back buffer and a depth stencil. So I just add those in here to be available for anyone who inherits from render graph. And you can see them just being set up here. When you create the render graph, you have to pass in graphics, and the back buffer target is just get target from graphics. And the master depth, it just creates an output only depth stencil buffer. But yeah, that's the basic overview of how the system works. So, I mean, if we take a look at the most complicated render graph that we've created so far, and we see how it looks in our new system. I mean, we already understand clear render target, clear depth stencil. They're just going to clear those buffers at the beginning of the frame. We do our Lambertian drawing. This is a render queue pass. So jobs from our geometry are going to be submitted here. Then for the outline, for generating the outline mask, jobs are submitted here. This one, interesting enough, doesn't bind the render target because it's only setting up the stencil buffer. So this one binds the depth stencil from here, adds the masking to it. The next pass here is going to require a texture in from our outlining stuff here. So this is also a render queue pass. It gets geometry and it just does the solid drawing. Notice that this pass actually owns its own concrete resource. This is an off-screen render target, and this is what is going to be all those outlines, solid outlines are going to be drawn to. This also might be smaller resolution than the back buffer, drawing to reduced resolution. Then this thing is going to be bound as a texture to the next stage. So we see this source here is actually, it's not a buffer source, it is a bindable source. And that is going to source this as a texture to this one, which also has a second off-screen render target. And it is going to do the horizontal blur on that. And it is actually sharing some constant buffers. So you know that the horizontal and the vertical blur, they both need the kernel and the blur direction. So we're going to share, instead of having two separate ones, we're going to share them between these two passes by making them global. And these global bindables can be sourced into the horizontal and the vertical pass. So it has its own buffer here, and that is going to be bound as a texture into this pass, along with the kernel, the direction. It's got its render target, it's got its depth stencil, and it composites the image from this full screen texture onto our render target and outputs that, and that's the final output to the system. Notice that in the global render graph, I make the back buffer both a source and a sink. And I just do this to ensure, because all sinks must be bound, by making this a source and a sink, that means that you just ensure that some pass must finally target this sink, and that just ensures that, you know, the logic of the render graph makes sense. Something is indeed finally being presented to the user. But yeah, that's the basic idea of the render graph for that scene. And again, if we look at the blur outline render graph, it inherits from render graph. It has some constants here for the Gaussian blur. It has a helper function that sets the Gaussian blur, and it has two shared pointers that hold the global blur kernel and blur direction. And then if we look at the constructor, we just see it just sets all those passes up that were in that diagram I showed you. The clear passes, the Lambertian depth stencil feeds into the outline mask. Then we're going to set up our blur constant buffers for the kernel here and for the blur direction. We construct those constant buffers, and then we add global sources for them. So now they are in the pool of global sources. We create the blur outline drawing pass, and remember, this pass has its own internal render target, so it actually doesn't have to declare any sync targets. It's just purely a output for future passes. So we create it, we append it, then we have the horizontal blur and the vertical blur, and they have to target the texture that was output from here. So outline draw dot scratch out, and they also want to target the global constant buffers. In the final vertical pass, many things have to be input. The overall render target, the overall depth stencil, the full screen texture from the horizontal blur pass, and those constant buffers for the Gaussian. And then finally, when you've appended all the passes, you have to, for the global sync, you have to tell what that global sync targets. So the global back buffer sync targets vertical dot render target. And then the circle is complete. The swap chain is finally rendered to from this. And that's it. And then the helper here, set kernel Gauss. This is just the same stuff from the previous video. Nothing new there. Just a little helper, which you can add to your render graph classes if you like. Add some helper functions or whatever. Just some organization stuff. Now, as for what has changed in the other parts of the system, not a hell of a lot. The major change you're going to see here is, so in step, before, we targeted passes by their index. And then we would, when we submitted a pass to the frame commander, we would just say, or we submitted a job to the frame commander, we just say, submit this job to, you know, pass of index 0 or whatever. But that's not very good because, you know, numbers, like you could change some code and forget to change the number and it would still compile and run, but the result wouldn't be correct. And it might be hard to debug. So what I've done is I've made them target by pass name, and that name is validated. So when you create a step, you have to tell it which pass name in the render graph it targets. And then once the render graph is all built up, you have to link your steps to your render graph. And all that linking does is it calls a function on the render graph, getRenderQueue, and that returns you a reference to a render queue pass of that pass name. If it can't find a render queue pass in the render graph with that name, it's going to throw an exception, which is good. That'll let you know that something's wrong. Maybe you changed your render graph, you forgot to change a technique, and now it doesn't target the right thing. And then we just use pointers. After we've linked, we use pointers to point directly to the render queue that you're going to submit to. So now when you submit, You just use that pointer to the pass. You call accept. You pass it the job. That's the main difference. We're linking instead of declaring the link by index, we declare the link by a more descriptive string, and then we validate those string links and we resolve them to pointers. And of course, this is only going to be called once. It's not going to be called every frame. The other major difference is for the depth stencil and a render target, I make them inherit from bindable. So I make it so that they can be owned by a shared pointer to bindable. That fits a lot better into the render graph system. But they're distinct from other bindables in that they also inherit from the buffer resource interface. So depth stencil and render target, they have a dual interface. They inherit from bindable, but they also inherit from buffer resource. And buffer resource has the ability to bind something as a buffer and to clear the buffer. And again, that just works a lot better with our render graph system with the sinks and the sources. All right, the final topic that we're going to quickly touch on here before we wrap things up is that thing I alluded to a little earlier. The difference between, buffer sinks and bindable sinks, buffer sources and bindable sources. Because I've made a distinction here. I've got separate classes, but I haven't really, explained why we have these two different concepts. So if you look at the connections here between the passes, you'll see I've used a little bit of a color coding scheme here. We've got red connections and we've got blue connections. That's not just some random thing I did. So the red connections are for buffers, things like the render target and the depth stencil. And that is quite a bit different than these blue ones. These blue ones here are bindables. And you might be saying, well, Chili, isn't this here a render target? Yes, it is a render target. The resource itself is a render target, but it is being exported as a bindable, because think about this here, this scratch in, it's not taking that in as a render target because the render target is this thing here. It's taking this in as a texture, which is a very different story. So when you look at this diagram, when you think about, how a render graph works in general, it's tempting to think of these all as, inputs and outputs, right? So this clear render target takes this buffer as an input and it outputs a cleared buffer. This Lambertian takes it as an input and it outputs a render target with, stuff drawn onto it. But it's actually fundamentally different when you think about it in terms of the pipeline. If we look at the pipeline, this render target, which was rendered to from this pass, is going to be bound to the pipeline of the horizontal pass to the pixel shader, right? As a texture. Bound as a pure input, and then the output is going to go to this render target here. And then this render target is going to be bound as a pure input to the verticals pass. But what's happening with this one? Well, this render target is being bound as the output here of this stage. And then when it's passed on to this stage, it is also being bound as the output. So is this an input or is it an output? It's kind of weird with these buffer resources. If you look at the graph, it seems like it's an input here, and then it's also being output here. But when you look at what's happening with the render graph, it's always being bound as an output. And yet it's useful to think of the render target as being bound as a, an input and output, or as being, a sink and a source. And the reason why is because there is dependency and there is ordering in how you bind these. So, the way it works is you have these passes and they're each going to bind the render target as an output, and they're going to add their shit to the render target. Or in the case of a clear, they're going to clear the render target. But they're each going to have an impact on the render target. And those impacts, they have to be ordered specifically. You can't swap the order of, the outline compositing pass and the Lambertian pass, because you'll get a completely different result. Obviously, you can't swap the ordering of this one here, the clear pass, because if you clear at the end, you're going to get a blank screen when you present it. So So there's dependency here, there is ordering, and because there's dependency and ordering, it's very useful to hook them up in a serial fashion like this. Even though what's happening is different passes are just pooping on the same plate. It's not true input-output, but it's useful to model it like input and output. Now, because of these differences between bindables, pure input-output bindables, and buffer resources, there are different requirements on them. For example, in a buffer resource, a single source can only source to a single sink. You can't have this source supply this sink and supply a different sink at the same time. It doesn't make any sense because there needs to be a very specific ordering. This one should have to supply this one, and then this one would supply this one to make the ordering clear and explicit. But for bindables, for pure input-output bindables, the ordering doesn't matter. You render to this render target, you have this texture. The guys who use this texture, they're not changing it, they're just reading from it. So you can source this texture to however many passes you like. And that changes the behavior of these different sources and sinks. So a buffer source has to make sure that only one sink is targeting it. But a bindable source can have any number of sinks targeted. So because of these fundamental differences between these two types of resources that are shared between passes, that is why I split it up into buffer sink and bindable sink. On the other hand, you have, buffer source and bindable source, and it's the same idea, same story. And you can see here, I add this static assert here to enforce that. The template type T has to derive from buffer resource, and here, template type T has to derive from bindable. And similarly, on the bindable side, you have yield buffer and yield bindable. So if you try to call yield buffer on a bindable, it's going to throw an exception, bad things are going to happen. And that's how I enforce that separation. That's how I make it so that if the person who is, crafting the render graph, they're writing the description of the render graph, if they screw up when you try to build that render graph, you're going to get some diagnostics that are going to help you figure out what you did wrong very quickly instead of, spending a few hours in the debugger. Now, the final piece of the puzzle is the container bindable sink. This is a special sink. Source doesn't have a container bindable source. So only sink has a variant that works with containers. And the basic reason for that is, well, if you look at the pass lib, if you look at the binding pass, it has a vector of shared pointers bindable. And what I would like to be able to do is create sources that link into a bindable in this vector. But if you know anything about containers, you know that when they grow, pointers get invalidated and references get invalidated. Well, what do sinks use to link up with the resources? They use a reference to a shared pointer. So if you try to take a reference to something that's in a container, you run the risk of that being invalidated. So we create a special sink that works with containers. And what it does is, instead of storing a reference to a shared pointer, it stores a reference to the container plus an index, which is better. So that makes it so that if you grow the container, you won't invalidate. It's not perfect, by the way. If there were some way that you could reorder or resort the bindables in the container, you would have problems. But for our system right now, this works very well. And again, this is the reason why you can do this, and I could just inject this into my system without having to change everything else, is because I all inherit from a polymorphically, from a base interface. It was very easy for me to add this special case in here to be able to work with those containers. But yeah, that's why this exists. It exists only for the purposes of being able to create sinks that target something in the bindable container for a binding pass. And that's the reason why you've got this template function in here, add bind sync. So you've got a function add bind, and it's very simple. It adds a shared pointer into this vector of bindables. But you've also got add bind sync. And what this allows you to do is you can put an empty shared pointer into this bindables, and then you can register that as a sink that will be filled by some source. And this uses the container sink. So because we're adding the shared pointer into the container at the same time that we're registering the sink, we know the index in this container is just going to be the index before we add that shared pointer. So we can capture the index by using binds.size. Then we add the empty shared pointer, and then we link this sink, the container sink, to that shared pointer via the index and a reference to the container. And then if you look at something like the horizontal blur pass, you can see that being used here to add a render target sink that will take the scratch in, and to add a sink for the kernel. And I mean, if you run it under the new system, you'll see it works like it was working before. There's no surprises or anything. It works exactly the same, except under the hood now, it's using a system where we're composing these different passes, and where we have a nice regular kind of format that we can describe them in. And under the hood, we have a lot of validation going in there. So if we screw up how we have built our render graph, it's going to tell us. It's going to point us in the right direction. And you might think, wow, this is a lot of stuff, Chili. And it is, but it's also kind of just the tip of the iceberg of what you can do once you have a system like this in place. There's so many things that we could do, and we're going to explore probably some of them in the future, but certainly, not next video or anything. I'm just going to add features to this system, every now and then as it makes sense. But let me just quickly talk about some of the crazy things that you can do with this. So, I mean, if you look at how we describe our render graph here, you can see it's a pretty regular system of describing how these different passes, hook up to each other. And what you could do is, instead of, doing it in C++ code like this in a constructor or something, you could make a separate file format, something like JSON, that describes it, and you could load that and then do that at runtime. You would have to recompile your program every time you wanted to add a new render graph. You could not even have to restart your program. You could just write a render graph in text and load it right in the program without having to restart. Pretty cool, huh? And once you got this ability to work with your render graphs in terms of data instead of code, it's not a big step then to make a graphical editor for your render graphs. So you can visualize a render graph graphically, and you can change the connections and add passes graphically with the mouse. And if that seems insane, I mean, just look at this. This is a plugin or a library for ImGUI. And so this already exists. You just have to hook this GUI system up to your render graph, and you could be creating render graphs like this graphically in your own engine at runtime. Other thing is, like what we're doing here, we have to add our passes basically in the order that they'll be executed. If we add them in the wrong order, the render graph system will tell us that it's bad. But what we would want to do in the future is we could just throw our passes at the render graph compiler in any order, and the system would then, by looking at the dependencies, figure out what order they have to be executed in, figure out which ones are independent and can be executed in parallel, and which ones have to be executed after each other. And they can also look at the resources that are required. Like if you have a bunch of different passes that are rendering to off-screen surfaces, maybe you don't have to have, 50 different textures for each of those. They can share them. And a system that can, analyze the render graph can figure out, how resources, exactly how many you need, and which ones can be reused and which ones you need different copies of. And lots of other things. One of the main issues that I come into when I'm building these render graphs and just building effects in general is I forget to bind something to the pipeline. And so the previous thing that was bound just stays bound. And sometimes I figured out right away, it just looks bad. But sometimes the thing that was previously bound works. And so you write some code and it works, even though you forgot to bind something. And then, 2 weeks later, when I changed that thing that was previously being bound, when I remove that, it breaks my system. But the thing that broke it wasn't the removing of that thing. It was originally I wasn't binding what I should have been binding to the pipeline. And so what I want to do is I want to create a system that tracks what should be bound. You can describe, every pass can describe what it binds and what it expects the bindables in its jobs to bind. And it can validate those things. and it can tell you immediately if something is not being bound that should be bound, or if something is being bound twice when it should not be overridden. And like look at this thing here. We've got a vertical pass, we've got a horizontal pass. I'm thinking I could make a composition system where I could create passes that are actually mini render graphs within render graphs, compositing this horizontal pass and this vertical pass into a single composite pass. And then you could use that as a building block in more complex render graphs. There's so many things I've got a big list of them here. I'm not going to go over all of them, but I think some of them, at least some of them, perhaps many of them, will be making their way into future videos. The main thing we got right now is we got our render graph system. We can create reusable pass components, throw them together in a render graph, and we can give them names and use those names to link them together. It's a beautiful thing. In the next video, we're going to be doing something else. I'm going to be showing you a whole bunch of different little tips, small tricks, stuff like that. And after that, we're going to be making a very concerted effort towards, doing some rendering with dynamic shadows. But until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, helps a lot. And I will see you soon with some more Hardware 3D.